So welcome back. This is our fourth video about the Markov networks, and now we're going to talk about the local independency. When we have a Markov network and we have a missing edge in the graph, it means that we have some sort of independency. So if you think about the undirected graph G that is composed by a set of vertices and a set of edges, if you have one missing edge, so that will be like this, x, y, going to be an edge that is not present in the set of edges, it means that x is independent of y given all the variables, all the nodes, minus x and y. So what I'm saying here is that, for instance, we have a missing edge in here. So it means that E is going to be independent of F given all the other variables that we have in the Markov network, not including, of course, E and F, because it will not make sense. So you're going to be independent, E is going to be independent of F given A, B, C, and D. So this is what we call a local independence, because it just mentioning two variables. So we're going to say that E is independent of F given some other variables. So we are just stating the independences between two variables. And we call this the pairwise Markov independence of G. We also have another local property of independence that is the Markov blanket. And we haven't seen this before in the context of Bayesian networks. So the idea is the same, right? That the Markov blanket is a set of variables that when we observe this set of variables, you're going to make x independent of the whole graph. So we can see one example here. We have the variable x that is here. If we observe the Markov blanket of x, that's going to be all those variables here that are neighbors of x, then I'm going to isolate x from the remaining of the graph. And you probably remember when we saw this idea of Markov blankets for the Bayesian networks. And in the case of the Bayesian networks, the Markov blanket was a little bit complicated because it was composed of the children of x, the parents of x, and the spouses of x. But now for the Markov networks, the Markov blanket is very simple. We just take the neighborhood of x, and that's going to be its Markov blanket. So these two interpretations of independence that we saw in the previous slide that we call the local independencies. We say that they are local because we are expressing the independence between two nodes, or we are expressing the independence of one node regarding its neighborhood. But we would like to have something that is more global. We would like to be able to ask if one node is independent of any other node that we have in the network, given any other nodes that we want to observe. And that's going to be achievable by an algorithm that we call the separation. And the separation algorithm, it's basically the same idea of a d-separation. So when we formalize it, we're going to see that it's the same idea of blocked paths that we have between nodes. So we can formalize the separation algorithm in the following way. So let x, y, and z be disjoint sets of nodes in a graph G. So it's very important to be disjoint, otherwise we cannot talk about independence. So we cannot say that A is independent of x given A. So these three sets must be disjoint. We will say that x and y are separated by z, and we're going to write it like this, separation of x, y given z. So we put the z here in the middle. So it's going to be sep g, referring that is about one specific graph G of x, z, and y. If and only if every path between x, a node in x and a node in y is blocked by z. And the path is blocked by z if at least one valve in the path is closed by z. So we saw in the Bayesian networks that is going to be a little bit more complicated because we have one exception of the convergent structures. But in the case of the Markov networks, the path is going to be blocked if we have one observed node in the path. So for instance, if I want to test if E is independent of B, we're going to check for all possible paths. So we're going to have one path that is going to be this, and the other path that's going to be this. And those paths are going to be blocked if we have one node that is observed in the path. So for instance, if we observe C, the paths will be blocked. If we observe just A and not C, one path will be blocked, but the other one will not. So in this case, we cannot state that they are separated. But if we observe A and D is here, we're going to again block both paths, and E is going to be independent of B. So just to write this down, right? So in the first case, we can say that E is independent of B given C. That is correct. We can say that E is independent of B given A and D. And that's a very simple algorithm that it's much easier to understand compared with the version that we had for the Bayesian networks. Okay, and as we had with the Bayesian networks, this definition of the separation algorithm is not very efficient because we need to consider all possible paths that are connecting a node in the set X and a node in the set Y. And we may have an exponential number of paths. So we needed to have a more efficient implementation. In the case of Markov networks, that's going to be very simple. We can use the idea of cut set test. And this cut set test is very simple. Actually, what we're going to have is to prune the nodes that belong to Z. If you have a graph like this, and we're going to test if X is independent of Y given Z, and we're going to go to the nodes in Z, and we're going to prune those nodes from the network. So they're going to block the influence. And if Z is a cut set to this graph, it means that you're going to split the graph into two parts in a way that we start a depth first search from the nodes here in X, we are not able to reach the nodes in Y. It means that X is independent of Y given Z. It's interesting to discuss the soundness and the completeness of the separation test. And this again equal to what happened with the Bayesian networks. In a few words, the separation test is sound, but it's not complete. What does it mean? It means that if we have a probability distribution P that's induced by the Markov network, if we find that the nodes X are separated from Y given Z, it means that X is independent of Y given Z in the probability distribution P. So in other words, we can safely use the separation test to derive independent statements about the probability distribution P. All right, that is a good result, but we need to know that the separation test is not complete. It means that the lack of separation between two variables does not imply into dependency. And the reason that happens is the same as it happened with the Bayesian networks, is that we may find independencies inside the parameterization of the Markov network. So this is one example, right? So in this case here, A and B are directly connected by one edge. At the same time, because we expressed the relationship between A and B in this form here, just with a constant number, it means that A is independent of B. And you can actually compute the joint distribution and check that for yourself, but it should be very clear, right? So if we look at the values of A, let's suppose that we observe that A is true, so we have these assignments here. It doesn't change anything about B because B and not B will be associated with the value 1. In the same case that if we choose not A, again B and not B will be 1, and if we observe B, like B true, it not changing anything for A, and B false as well. So it doesn't matter what we choose to one variable, it not influence the other one. So these two variables will be independent. But they are independent into the parameterization of the network. They are not independent in the graph. Actually, in the graph, they are directly connected by an edge. So they will never be independent just looking at the graph. And this is one expected result because like this separation algorithm only looks at the graph structure. So it cannot infer anything about the parameters. So it is limited to what is being observed in the graph structure. So now that we are used to the idea of the Markov and the Bayesian networks, we can make a small comparison between these two types of graphical models. So let's start with the Markov networks. So first, the factors tend to be easier to change if compared with the Bayesian networks because we have a no normalization. So we don't need to care about if we change one number, if we have to make all the numbers to some 1 or something like this. But it tends to be a little bit more difficult to elicit. So if we ask person about those numbers, because it doesn't have one very simple interpretation, it's going to be an idea of influence between two things, but we don't have a minimum and a maximum, so it tends to be a little bit more complicated for people to express those numbers. Something that's good about the Markov networks is that we can apply to problems that have cycles or has no natural direction. So it tends to be a benefit compared with the Bayesian networks. One problem is that it's difficult to read the factorization from the graph, but we can always use the factor graphs. But we know that one graph can give rise to different Gibbs distributions, and so just look at the graph, we cannot figure out what is the factorization that we're going to be using in the problem. Finally, we know that the numbers that we compute with the Markov networks are not normalized, so we need to normalize them. And normalized numbers require computing the z, the partition function, that is the sum over all the entries that we have in the table. So if we naively compute z, we're going to see that using the full joint distribution, we're going to see that it's going to be exponential in the number of variables. But we can compute z in a directed way. So we're going to see when we study the variable elimination algorithm for the Markov networks, we can get z in the process of eliminating the variables. So for the Bayesian networks, we can say that the factors, they tend to be easier to elicit from people because many people are used to the idea or the concept of probabilities and can express these local probabilities in an easy way. And we have the limitation that we cannot have cycles in the Bayesian network, and also the edges have a direction. And sometimes we work with applications where the direction of the influence is not clear. So it would be better to use an indirect edge. So the graphs tend to be easy to interpret, particularly if we have the causal interpretation of the graphs. And they are naturally normalized, so we don't need to compute the partition function. And finally, we can use a sampling procedure to generate synthetic data from the Bayesian network. We're going to discuss more about this later on, but this is one characteristic of the models that we call the generative models. And the Bayesian network is one example of a generative model. And the generative models, they have this name because we can easily use them to generate synthetic data. So we can understand the Markovian and the Bayesian networks as a sort of languages to represent the dependencies in probability distributions. And it's interesting to note that those languages can represent different sets of independencies, so they are not redundant considering each other. So it would be very uninteresting if that was the case, because we could just use a Markov network or the Bayesian network. It wouldn't matter which model we decide to use because both models would be able to represent the same independencies. But it's a lot more interesting in the case that we have the set of independencies that this language can express in the case of the Markov network to be slightly different from the set of independence that we can express with a Bayesian network. Of course, there are sets of independencies that we can express with both languages, but there are also some set of independence that we can only express with the Markov network and others just with the Bayesian networks. So we have here some small examples where this happened, and this example here we haven't seen before in several lectures. So this set of independencies can be easily represented in a Markov network. But if we try to represent these in a Bayesian network, we have problems, right? So let's suppose that we do something like this, x1 and x2, and we have y1 and y2. And we decide to do like this. Well, in this case, we can say that x1 is going to be independent of x2 given y1 and y2, exactly as we wanted to happen in the first independence there. But when we look at the y1 and y2, because we have this V structure here, right, it's not true that y1 is going to be independent of y2 given x1 and x2, because when we observe x2, we make this convergent valve here to be active. So we'll be able to influence y1, will be able to influence y2. And we can try to change the direction of the edges here, like change this edge here to this direction, but now we're going to have a convergent node over y2. And we can try to remove some edges. In this case, we're going to make additional independence assumptions. So we will not be able to find a Bayesian network that has exactly this set of assumptions. In other words, we cannot find a Bayesian network that is a perfect map for this set of independencies. But the opposite also happens to the Markov networks. For instance, if we have this independence here, that x1 is independent of x2, and that is easily represented by this Bayesian network, we will find it difficult to represent in the Markov network. So for instance, we could try to do something like this. I have x1, I have x2, and I have y here. But in this case, x1 is not independent of x2, so I cannot guarantee this. And also, we're going to see that x1 is going to be independent of x2 given y. And we can try to fix that by, for instance, removing some edges. So I try to remove the edges here. In this case, we will have that x1 is independent of x2, but we also have other independence assumptions. For instance, x1 is going to be independent of y, and x2 is going to be independent of y. Okay, and finally, there are many occasions that we need to find a Markov network that's going to be an IMAP for the Bayesian network. So that situations occur, for instance, in the case that we want to convert the Bayesian network into a Markov network in order to do some sort of operations, for instance, some sort of inference. So that's very common to happen. So in this case, we may not find the perfect map. We may not find a Markov network that is a perfect map for the Bayesian network. What we do is to find a Markov network that is an IMAP for the Bayesian network. And one very simple way for doing that is through something that we call the modalization. So the modalization is when we take the parents and put an edge between the parents of a unmarried child node. So actually, it should be here, child node. So it is the case that we have in here, right? So we have this. Bayesian network here. We have these two parents that are not married, so we're going to marry them, put an edge between them, and we get this Markov network here. Of course, this Markov network is not able to express the independence that we have in this Bayesian network, but this Markov network here in the bottom is an IMAP for the Bayesian network. And what we lose exactly this independence here. Okay, so I think that is enough for this video. Let's take a break, and I'm going to continue in the next video when we're going to discuss the variable elimination algorithm for the Markov networks. See you soon.